Hello, my name is Sina Kuseri, and I will today give you a presentation on my manuscript on active control of air suspension systems in commercial vehicles. First of all, I will give an overview on the air suspension systems, active suspension systems. Then we will discuss the system dynamics, and then I will show you the numerical simulation outcomes and the conclusion. Okay. Commercial vehicles such as public transportation buses can benefit from height control of the chassis that an air suspension provides. Main benefits of height control are retaining a pitch angle parallel to the road for passenger comfort, regardless of the load and road disturbance, and easy accessibility to vehicle for especially old or disabled people. Electronically controlled air suspension systems, actually it's shown as ECAS, are commonly used in commercial vehicles to enhance ride comfort and improve handling stability. In this paper, we propose a basic PID controller for height adjustment and road disturbance rejection of ECAS. And it is shown that this basic controller is effective and acceptable with acceptable performance. Okay, now I will introduce the system dynamics. You see the pneumatics of the ECAS system schematics, and the displacement of the sprung mass, which is the vehicle, is adjusted by inflating and deflating at the air springs, which modifies the vehicle's height to achieve the desired driving performance. During inflation, compressed air from the reservoir is directed into the air springs through the pipeline, raising the vehicle's height. In the deflation process, air is released from the air springs into the atmosphere via the pipeline, lowering the vehicle's height. In driving the system dynamics, we have the following assumptions made during the derivation. We treat air as an ideal gas and its kinetic energy is considered negligible in all air springs. The pressure within the air reservoir remains constant during the operation and there is no gas leakage from the system. The solenoid valve is modeled as a throttle. Actually, it's an orifice. The pressure and temperature of the gas in the air springs are assumed to be uniformly distributed. Rate of change of the volume and the effective area of the springs are constant. Okay, that's the thermofluid model. And as you see, the solenoid valve in the gas circuit is simplified as an orifice. So when the solenoid valve is open, area normal mass flow rate through the valve is given by the equation number 1, where the definition of the parameter phi changes upon the choked and unchoked flow conditions. You see the flow can be in a linear condition if it is, as you see, the PD divided by PU actually is less than a critical value. Actually, the upstream and the downstream pressure ratio is defined as the critical ratio. And as you see, if the flow is choked, we have the linear flow condition, as you see in the first equation, and it's the unchoked condition in the second case. Okay, so the variable mass thermodynamic model of air spring is derived to obtain a relationship of air pressure and the area normalized mass flow rate of the pipeline. The charging and discharging process of the air spring is independent of each other and they are relatively fast, so they can be regarded as adiabatic process as shown in the equation number 3. In this equation, the rate of change of the volume of the air spring is given by the equation number 4, and actually so you see that it is equal to the rate of change of height times the change of volume with respect to the change in the displacement. Okay, the mechanical model is shown in the figure. That's the quarter car vehicle model. We have the vehicle and the tire as shown. And this is the equation of motion for the quarter vehicle mechanical model suspension system. And actually, this the quarter vehicle, the M1, can vary actually, depending on the load on the vehicle, the number of passengers. Okay, after we have established the system dynamics, we made the numerical simulations. And actually, in the numerical simulations, we provide an input to the system. The first thing is the rough road condition. It's modeled by a first order filter that takes a white noise as the input. So you see it's a first order dynamics. Okay, bump on the road is modeled by the equation as shown in the as a sinusoid in the equation number 7. And we take only the half period of the sine signal to represent the bump. Actually, the input disturbance signals given in during the simulations are given in the figure, where left-hand side is the rough road and the right-hand side is the bump. Okay, during the simulation, we have some parameters of the suspension system given actually from a reference. So this table gives us the parameters used during the simulations. Okay, so the first output is the response of the active air suspension system to a bump and to rough road disturbance as shown in the figures. When passes over a 50 centimeter height bump, vehicle height rises 5 centimeters during the transient response, as shown on the figure on the left. Hence, ECAS system bump suppression performance is 67%, and bus reaches the steady state in 3 seconds, as shown on the figure on the left. And the road disturbance model is a pseudo-random signal taking values in the range of plus minus 3 centimeters. The ECAS system is so adjusted that it does not take any action if the disturbance is within plus minus 2 centimeters margin. If the road disturbance exceeds this margin, controller activates air valves and bus height is adjusted. Actually, this mode is the main benefit of the active air suspension over the passive air suspension systems used in general. Actually, and frequent switching of the air valve in passive suspensions can cause premature wear of the components. And moreover, high energy consumption of the vehicle to generate compressed air is mitigated. Actually, this is the main advantage of active suspension system. Okay, the ACAS system also enables the driver to adjust the height on the bus. So simulated height adjustment process are given in the figure, and you see that the green line is the target height in the simulation, which is 75 centimeters during ascent of the vehicle body and 25 centimeters during the descent, as shown on the right-hand side. Without feedback control system, height is elevated to 80 centimeters during descent. Okay, as you see, the red line, which is 5 centimeters above the reference comment. Feedback PID control achieves almost zero steady state error. Actually, it's the blue line that we see on the left-hand side and also on the right-hand side. So during the descent, there's also an error, you see, without PID control. And PID control gives us zero steady state error. Okay, our conclusions of the study is actually we have seen that the implementation of ECAS in public buses addresses the critical need for adaptive suspension solutions that can respond dynamically to varying load conditions and road surfaces, thereby optimizing passenger comfort and vehicle stability and passengers' accessibility by height adjustment. The ECAS system used with the system specified in our work had a suppression performance for the bump on the road up to 67%. And we have shown that the feedback PID control leads to zero steady state error during the height adjustment process. And finally, it is possible to deactivate the air valves if the road disturbance is less than a margin that can easily be tolerated by the passengers. Frequent switching of the air valve in passive suspensions can cause premature wear of the mechanical components. Moreover, high energy consumption of the vehicle to generate compressed air can be mitigated. Thank you very much, and I can answer your questions if there are any.